Hi, my name's David Hardy. I am Power and Cooling Product Manager in the Power Edge team at Dell. Thanks for joining our session today on advanced cooling. So one of the challenges that customers are seeing today and will increasingly see in the future are power trends up and to the right. CPUs in particular, we're seeing CPU TDPs for our current generation approach 300 watts with the Milan and Ice Lake processors. Next gen will go even higher. Other components contribute a high system power as well. Memory, NVMe drives, and particularly the increasing use of GPUs. The result of having higher component and overall system heat is that for air-cooled systems, the fan power associated with moving enough air to cool these can reach as high as 20% of the total system power budget. And in some cases, either in dense configurations or with particularly challenging components, air cooling simply isn't enough and liquid cooling may be required. From our perspective, we see the transition points to be for dense compute solutions, typically used in high performance compute environments. Many of these systems are using liquid cooling today because the CPU TDPs in the 200 watt range, if you have a densely configured system configuration, you still may be required liquid cooling today. For the more common monolithic platforms, typically a 1U solution can cool up to roughly 300 watts without any problem using air. Now, if you use very cool air, you can exceed that 300 watt limit. Or if you don't have a very densely configured configuration, you could also have a higher TDP part, but that's a ballpark number that we're seeing today. For 2U systems, given the larger volume inside the chassis, you can cool up to 300 watts in a very straightforward manner. But what this is pointing to, since CPUs are eventually passing these thresholds, is that eventually liquid cooling will be required on all manner of systems. Today, we see a lot of system rack power levels that are mostly in the 10 to 12 kilowatt per rack range. Now, while these are pretty easily air cooled, once you start climbing up towards 20 kilowatts per rack again, you start reaching a point where the amount of fan power being consumed to cool these devices is significant enough that you're actually carving out power for fans that would be better utilized for servers running operational tasks, running your workload. When you get well above 20 kilowatts into the 30, 40, 50 watt range, kilowatt range, and you're really seeing situations where, again, you need either particularly cool air, an exceptional amount of fan power to cool these systems, but in general, liquid cooling is effective and much more energy efficient means of cooling these denser racks. So why liquid cooling? Well, air is a liquid, or rather air is a fluid, and it captures heat. It's just that liquid captures heat much more effectively than air. So by capturing the heat more easily, keeping it in its keeping that heat energy in the liquid through heat transfer to the facility water loop, it's much more effective at capturing and removing that from the data center environment. And the last thing to point out is, as most people who've been in data centers know, IT fans spinning very fast generate a lot of noise and will pump out a lot of heat into the hot aisle of data centers. So shifting that to liquid not only is more effective, but it makes for a more pleasant experience for people actually working in the data center environment. So Dell's perspective on liquid cooling is that we want to support customers with whatever stage they're at, whatever rack power densities they're at. It's all about what's most relevant for you and what's the most efficient and appropriate solution for the IT that's running your workloads. So today, the vast majority of customers are still implementing solutions that fit on the traditional line, which is using air, being smart about containment, the separation between hot aisle and cold aisle in your data center is a fundamental starting point. There are ways to augment your air-cooled data center using in-row cooling or using rear doors, which use liquid to do the heat capture again, but are spot solutions. And what I mean is you can place these in a particular area of the data center that needs help, for example. The solutions below are what we would call the more advanced forward-looking solutions. These will include direct liquid cooling, which is standard on Dell servers today. We'll go over that in a little more detail. And there's also immersion cooling. This is a partner-led solution from the Dell perspective, but we are working with partners to make sure that we've got solutions that customers can deploy and leverage all solutions that are out there today. One of the reasons that Dell is a fan of direct liquid cooling is it leverages warm water. And by warm water, what I mean is the temperature of the facility water that is going to be involved in the heat exchange between the IT and external to the data center can be as warm as 45 degrees C. What that means is you don't have to use chillers that require a lot of power to take the water temperature down to the 7 to 10 degrees C range. Chillers are typically used to create cool air in data centers. If you're able to eliminate a chiller out of the equation, your overall cooling overhead reduces by about 80%, which is a massive energy savings. Dell DLC solutions, as I mentioned, effectively cool the server line all the way up to the top TDP levels of our CPU stacks coming from Intel and AMD, leveraging warm water. In other words, our cooling overhead associated with DLC is that very efficient 12% level, as opposed to using chilled water, which can drive an overhead of 60%. Briefly, I wanted to make sure it was clear that when you operate a direct liquid cooled rack of servers, what you're really doing is setting up an ecosystem that enables these servers to run. What we have is an image here of racks of servers that are direct liquid cooled. The unit to the right is what's called a coolant distribution unit, and this is the main heat exchange element. The unit, or rather the lines to the top that show the purple water feeds that are the cool feeds to the IT. The red is actually the warm fluid exhaust that goes back to the heat exchanger from the racks of IT. What that represents is the coolant that will go at very low pressure, between 0.5 and 1 liter per minute, to the IT through the cold plate loops, capture the heat off of the CPUs, and then take it back to the heat exchanger where, as you can see, the two loops that are both in proximity in that central cooling distribution unit. What is happening there is heat is being exchanged to that lower loop. And what that lower loop represents is the customer's facility water loop. So in this case, the customer water could be a range of temperatures. There's a requirement for a maximum temperature and a minimum flow rate, which is well in the realm of what facilities managers are used to providing. But the two loops do not interact, and that's important because the coolant loop needs to remain very clean, pure, have it be closed loop and go through extensive filtration so that when it goes through the cold plates, there's no debris that can get caught up and cause any blockages. As long as it's isolated from the facility loop, that cleanliness will be maintained. The facility water loop doesn't really need to be as clean or highly filtered. It's going to be typical facility water that doesn't require the customer to do anything above and beyond what they would normally use that water for. But by capturing the IT heat and rejecting that heat to the facility water, which is then taken out to either evaporative towers, cooling heat exchange methods of some sort, you've got an environment that leverages a very high level of efficiency at extracting the IT heat and removing it from the data center. Here's an overview of what the actual server solution looks like for a direct liquid cooled solution. What Dell is offering today on our 15G platforms are cold plates that go directly onto the CPUs. We've got examples to the right. The top one is our 2U R750. As you can see, there are two cold plates. They're kind of a gray-blue color. There's one inlet and one exhaust line coming out the far right of that system. The lower solution is what's called our C6520, which is our 15th generation server node that goes into a 2U chassis. 4 compute nodes will fit in this 2U chassis. So it's our densest solution, very popular with high performance compute deployments. In both cases, the cold plates consist of the tubes, the cold plates that attach on top of the CPUs that replace the air heat sinks, and then those lines connect to rack manifolds in the back of the rack. One new capability with our 15G DLC solution is leak sense. What that does is detects if there's any condensation or coolant leak at the CPU. The leak will be detected by a board that's under the cover of the cold plate loop. It's best seen in the picture to the lower right. It's sort of a beige color, as you can see under the translucent plastic cover of the cold plate loop. And that would send a signal when it detects any drips to our software management, our iDRAC software management capability. If you have Open Manage Enterprise through Dell, you would have a high degree of control over what you do with that signal other than the simple iDRAC alert. Customers could pre-configure the node through OME to either shut down the node or to maintain operational status and alert somebody to come and inspect the node before it gets shut down. Here are all the components of a DLC solution. To the right, we have the server, as I just went through with the cold plate installed. These come out of the Dell factory, pre-configured, shipped to either an integrator's location or the customer site. The rack manifold is what is connected to the back of the rack. It's almost like a PDU for fluid. It's a vertical manifold that connects to the back of the rack that the servers connect to. The black tubes that come out of the back of each server will the connection to the blue cold line will match the blue connector on the server. The hot return would go to the red connection on the rack manifold and return that fluid back to the heat exchanger. The unit to the left is the heat exchanger, what we call the coolant distribution unit. This can come in a small size, such as a rack mount CDU, as we show in this picture, or for larger scale deployments, we can have the in-row CDU, which can drive, it's typically used to drive 5 racks or more of DLC gear. And that provides some scale economy if you're doing larger scale projects. But functionally, they do the same thing, in that as the coolant comes back from the IT with elevated temperature, it goes to the CDU and it exchanges that heat energy to the cold plate that's inside the CDU connected to the facility water. What then goes back to the IT is the cool temperature coolant that is primed to absorb all of the heat off of the CPUs. Here's our upcoming 16G roadmap for direct liquid cooled devices. As you can see, we have an extensive list of platforms that will be supported with direct liquid cooling to CPU at their time of launch. In addition to the CPU liquid cooling, we do have platforms under investigation for accelerator-based liquid cooling. As I mentioned on the first, or the slide where I talked about advanced cooling solutions, we do have partnerships with companies that do immersion cooling. You may have heard of single phase immersion. And what this means is the IT is immersed in a dielectric material that allows for full heat capture, as opposed to just having cold plates on CPU's GPU or memory. The tanks have heat exchange also to facility water, but the coolant that is pumped into the tank, again, is pumped from the bottom to the top, captures heat, and extracts it back to that heat exchanger. But there's no special equipment on the gear. There are no cold plates. The fluid will actually basically wash over the entirety of the server components. Two-phase immersion is a slightly more advanced capability where the fluid that the IT is immersed in actually has an engineered boiling point that allows for the fluid, when it comes in contact with a hot component such as the CPU, to boil off. That vapor rises to the top of the sealed tank and hits a condenser unit, which converts from vapor back to a liquid, and that liquid then will fall back into the tank. So there's a circulation of the fluid to vapor back to the fluid that's basically naturally causes a movement in that fluid. So you don't need any pumps to move this engineered fluid around. The reason why you would do a solution like this is the engineered solutions have an extremely high degree of heat capture capability, more so than the single phase immersion solutions. In that phase change, as an extremely effective way of managing heat at a component level. So these would be able to effectively cool future generations of CPUs and GPUs that the single phase solutions currently aren't designed to handle. To get this higher degree of performance, the systems are more complex. The systems in the fluid being used are a little bit more expensive as well. And in general, these solutions, from a business perspective, have not been deployed at the same scale as a single phase immersion solution. So it's a little earlier in their business cycle. But Dell continues to work with a variety of partners to make sure that we're participating with companies working on alternative cooling solutions and making sure that we've got the ability to help customers pick the right solution for their workloads and their data center environments. So that's the conclusion of my talk. And if anybody has any questions, I'd be happy to answer.